inviting me to give this talk. And now let me just arrange. Okay. So this is an overview talk on various aspects of that I think are important in the context of causal analysis in time-to-event settings. And as such, it's put together from different pieces of work, and some of you may have heard some of this before. So two aspects are the mediation aspect and the separable treatments aspect. But the other aspect is also that I want to talk about the importance of target trial emulation in the setting when we do causal analysis with time-to-event data. And there I want to acknowledge our working group here in Bremen that we call Causal, which stands for the German Pharmacoepi Research Database, JEPARD, target trial emulation for causal inference. And a lot of the work is done in collaboration of big teams from clinical epidemiology and from the statistics department, from our programmers and our data managers. So the program for today is I will talk a bit about the importance of target trial emulation in these settings. Then we come to the aspect of competing events and the notions of total and direct causal effects. Then this takes us to mediation and longitudinal and survival settings where the separable treatment effects, this notion of different S demands in this context becomes important, and we return to competing events and separable treatments afterwards. All of this going to be very high level, little formulas, and please feel free if there are any urgent questions to interrupt or ask in between. Hopefully I remember to stop maybe in the middle. First, as a motivation, I want to tell you about a study that my former PhD student, now postdoc, Malte Breitmeier, did on the evaluation of screening colonoscopy for colorectal cancer incidence. Now you might wonder how can screening help with incidence, but colonoscopies are special in that they, during the procedure, they also remove precursors of the cancer, and insofar the colonoscopies can be preventive. So it's not like usually with cancer screening methods, you only discover what's already there. Here you can actually prevent, and so it makes sense to look at incidence. But first, let's remember a little bit the causal parameters. I'm sure this audience doesn't need much introduction here, but in the simplest possible case, what's our causal S demand for a treatment effect when we have a binary point treatment, or if we do an ITT analysis with two arms, some outcome Y. Y bracket A is our potential outcome if we were to set A to one of the values. And what I like to highlight is that the effect is actually always conditional on the relevant subpopulation eligibility, characterized by your eligibility criteria, etc. There's no such thing as the causal effect. It's always in a relevant or available population. So this would be, for example, the average causal effect, a mean difference, but you could look at risk differences, risk ratios, etc. But more interesting in time settings is not only the outcome is often time dependent, but also the treatment is often time dependent. So let's look at more realistic settings, namely where treatment is a sequence of treatments, A1, A2, and maybe more. It's enough to look at 2 time points, in fact, to see all the complexities. So our counterfactual outcomes or our potential outcomes would be Y bracket A1, A2. This could be a time to event. Were we to set the 2 treatments, sequential treatments, to A1 and A2. And in this way, we might define contrasts. Let's say the event occurs by time t under always treat versus under never treat, 1, 1, and 0, 0 in the relevant or available subpopulation that you are studying. So that's what we would call a sustained treatment, and immediately the methods are much more complicated when we look at sustained treatments. And because we will talk about direct and indirect effects, let me also point out this type of contrast where we fix the second treatment at being definitely treatment 1 and 1 here, but we vary the first treatment 1 and 0, and this you could define or characterize as the controlled direct effect of early treatment controlling for later treatment. Okay, so we might wonder, is it worthwhile starting early, given that we will definitely start later with the treatment? It's a controlled direct effect, and it's also a sequential treatment setting. So returning to the example of a screening colonoscopy, the question was, how much does screening colonoscopy reduce, hopefully, the cumulative incidence of colorectal cancer? We also looked at different locations, but let's not go into details here. In the original paper, we looked at 11-year follow-up. By now, we have longer follow-up available. We have eligibility criteria regarding the age, excluding prior exposure, symptomatic patients, etc. And we use our German pharmacoepi research database, which is a claims database from 4 large statutory health insurance providers, and it contains data since 2004. So we have a long follow-up, which you need for screening questions. And the eligible participants here were around 300,000. So what is the S-demand? What would be the arms of a target trial? We could say we make our life easy and have a point treatment, binary point treatment that would be the treatment arm screening at the baseline versus the control arm no screening at the baseline. This is what we looked at in this original paper. And this means that especially the controls, they might go screening later, according to the rate that in the population people go screening to the colonoscopy, screening colonoscopies. This makes assumptions and methods a bit easier, but it's maybe a bit unclear the relevance to decision making, because whether you go now or later, yeah, this may be a bit vague. So arguably more interesting S-demand is the one where we say the treatment arm is as before, go screening at baseline, and then the control arm is never go screening. But of course, we do allow diagnostic colonoscopies if there are symptoms, and we can distinguish screening and diagnostic colonoscopies in our data. So in this case, the control arm is now a sustained strategy where we demand full adherence. And this is not something that you can even investigate in, not even in a randomized trial, because you can't force adherence. So adherence is not something that's randomized. Whether you have observational or randomized data, you will need adjustment. If you want to evaluate a sustained strategy, you need to adjust for possibly time-dependent confounding, and you need the data to make this plausible that you are really measuring all relevant time-dependent confounders. But the S-demand is more of a clear direct relevance to individual decision problems. So as you will know, if you're familiar with target trials, when we plan the study, we write down our target trial, and then we write down how we can emulate the target trial, how well we can emulate, what extra conditions we have. So here we specify, for example, our eligibility criteria, and this might be adapted to the available data. And here, the screening strategies that we are comparing, this is now the point treatment. So we compare screening versus no screening at baseline, and the same in the emulation. Ideally, we would randomize, but in real life, we assign according to the screening behavior at the baseline. Our time units are quarters of a year, so 3 months, because that's how the claims data is given. And randomization is then emulated via baseline confounding. So you can say that the contrast in a target trial would be the effect of being assigned to screening, whereas in the emulation, it's the effect of receiving screening, because of course we assign always screening and no screening in the baseline quarter. So these are fairly basic aspects, and we often say that the gold standards are randomized trials because they are randomized, but there are lots of other advantages of trials. For example, in a trial, you always have a clear time zero, but you don't have that when you use, not necessarily when you use health claims data, for example. To not go screening, you can do that at very many time points. So there's not a clear time zero. When is the first time that you don't go screening, right? So we have a non-unique time zero. For those who go screening, of course, then that's the baseline quarter for them where they go screening. We can define that. But where they don't go screening is not unique. So we need a solution. We can either come up with a definition that makes it unique, or we can just choose multiple baselines and conduct a sequence of trials and then pool across these different baselines, which has been shown in the literature to be the most efficient approach. Oops. Then, again, as I said, well, I'm not going into technical details. We estimate the cumulative incidence functions using pooled logistic regression, and we adjust for baseline covariates via inverse probability of treatment weighting. We did a sensitivity also with G-computation, sensitivity analysis, and it gave us similar results. And we obtained the confidence intervals via individual level bootstrap. So to illustrate, this is one person who goes screening here in the third quarter of 2007, and we start our trials here in the first quarter. Then they are representing the control group for the first trial. The second trial starts in the second quarter, and they fall into the control group. In the third trial, they fall into the treatment group. And afterwards, they are not eligible anymore because they've had a screening colonoscopy. So the same person can contribute to multiple trials, which leads to this efficient use of all information. And here we have the results, and for today it's sufficient to look at this plot on the right. Here we just have the two different locations. Here you can see the blue curve is the cumulative incidence, and note the very small scale of the y-axis. So this is the cumulative incidence over 11 years when screening occurs at the baseline, so under screening at baseline. Obviously, we are looking at incidence, so at baseline when they're screening, we discover a lot of cases. That's this bump. But then the slope of the curve is much flatter than in the control group, which is the orange group, which has a steady increase of cases over the whole time and ends up after 11 years to have more cases. So this is taken as evidence that the screening, both it discovers prevalent cases, but it also reduces incident cases by removing the precursors of the cancer. This is a typical shape of these plots that is also known from other studies. And the relative risk after 11 years here was 0.68. We checked our analysis with, for example, negative control analysis and various other sensitivity analysis. We also compared how much difference is there in adjusting for confounding. And there is a reason to believe that there isn't much confounding going on in the first place because there was not much difference. And the results are roughly in line with other findings. There's a recent pragmatic trial on this, and there are other target trial emulations with slightly different populations. Okay, but as I said earlier, maybe more interesting is actually the sustained treatment. So here we look at a sequence of treatment. So basically every quarter, people can either go or not go screening. And we would contrast a strategy where you go screening at baseline and then you can do what you want. Usually people don't go again for 10 years versus never screening. So this is 0, 0, 0 forever or for the duration of follow-up here. So of course, non-adherence, so when people deviate from this never screening is a problem. And the technique we use here is artificial censoring at non-adherence. And then, because this is a selection, we need to reweight to avoid the selection bias. Or you can also see this as an adjustment for dependent censoring because there are possibly reasons for not adhering to 0, 0. Mind you, this is an observation study, though people haven't been told to do this or that, and therefore adherence is a bit a funny word in this context. So we use inverse probability of adherence to this strategy to adjust for the artificial censoring. So to compare with earlier, we have the same person here who goes screening in the third quarter of 2007. So they are in the control arm for trial 1, but then they get artificially censored here where they do go screening. They're also in the control arm for trial 2, and again they get artificially censored here. And then they are in the treatment arm from then onwards, and then they are not eligible for further trials anymore. And this is the result that we obtain. Here you have just the baseline that I showed you earlier, and here I'm showing you the results with 14 years of follow-up, which by now, it's 3-4 years later now, we have 14 years of follow-up, and this is never screening. The treatment arm should look exactly the same, because there's no difference, and the control arm looks almost the same. It comes down a little bit because, of course, these people here might go to some screening where they get discovered as a case, and therefore there are a bit fewer here, but we can still see that there is a big reduction, relatively speaking, a big reduction in incidence here. So, but what exactly was the outcome variable here? I have been a bit vague about this. I don't know if you noticed. But what we are calculating here is, in fact, the total effect of screening on colorectal cancer incidence, because we are not eliminating death. We are not censoring. If people die, this is a relatively young population between 50 and 69, so there are not many deaths. But when they die, we do not censor them. And this is because we are targeting what is known as the total effect of screening. So death would be a competing event. This brings me to the second part about competing events. And this is inspired a lot by some joint work with Paloma, this PhD student, right now postdoc, I don't remember where she is now, in the context of dementia research, which of course happens with elderly populations where death is definitely an important competing event. So some examples of competing events, like many that we know, that where we would think this is a standard situation of competing event. For example, looking at the colorectal cancer incidence or dementia, competing event would be death from any cause. Or in other pharmacoepi safety studies, if we are looking at outcomes that are adverse events, especially in later life, again, death from any cause would be a competing event. But there are also maybe less obvious settings. For example, this was in the early days of the pandemic. People were looking at in-hospital mortality of severe COVID-19 patients, severely affected. And then a competing event would be discharge alive, because obviously not everyone is going to die in hospital. So something else happens, they recover, and that is then a competing event. Or if you're interested in the survival of patients who are on dialysis, maybe under different treatments or so, then if they get a kidney transplant, they are not on dialysis anymore. They basically move into a different state, which is maybe not what you're intending to study, and therefore this can be seen as a competing event. So let's be a little bit more formal. At least I'm using little DAGs to illustrate where we are going with this. So you can think of these as processes, and let's say M as a mediator, if you like, is the process that indicates whether people are still alive. And at different time points, you can imagine this continuing after 2 time points as well. And Y is indicating whether the person has had a colorectal cancer case, which obviously is only defined while they are alive. So here, the mediator would be survival. You need to survive in the first place, or you can prevent your event of interest by dying first, right? So How do we write this down a bit more formally? Let's think of our outcome as the time to the first of two events, E1 or E2. E1 might be death from cancer or colorectal cancer incidence. E2 is death due to other reasons. We could formalize this using counting processes that jump whenever the event occurs. And now the total effect in this case is the cumulative incidence or contrast of the cumulative incidence for event type K, so E1 or E2, whichever you are interested in. And this would be the probability that the first event is of type EK, E1 or E2, under your treatment strategy A. Now, point treatment or could also be a sequence of treatments. And so we might look at risk differences or relative risks here. This is very simple, actually. There's nothing complicated about this. It's non-parametrically identified when A is randomized. You just look at the relative frequencies, if you like, of these events over time. Note that we are not using hazards as causal contrast because of the many good arguments against using hazards as causal contrast in the literature. So this is the total effect. And when we randomize A, then the two cumulative incidences contain all the information that there is. So basically, if you have the two processes, MT and NT, I'm writing this in a shorthand notation here, A has been randomized, and you can always infer the effect of A on anything afterwards marginally. Everything else will always require assumptions, so even under randomization. And as we know, that what people like to do, a popular thing to do when there are competing events, is to artificially censor. Now, this is a different artificial censoring than what I mentioned earlier. To artificially censor at the competing event. But what this means is it corresponds to eliminating the competing event. So, for example, death due to other reasons or general death. And it corresponds to a controlled direct effect where we intervene to set our mediator process to be always alive, right? Remain always alive, or never. We force the competing event to not occur. And then we look at the effect on, after controlling for this, we look at the effect on the outcome of interest, the event of interest. So identification is a bit more complicated. First, obviously, we need baseline confounding, but we also need common causes of the two types of events. Okay, because we are also intervening, hypothetically eliminating by censoring in the mediator process. And you can either see it as a causal intervention or also as a violation of independent censoring if you don't include common causes of the two types of events. So let me illustrate this graphically. So if we are looking at the total effect, then what is maybe often overlooked and you must be aware of when we look at the total effect of A on the event of interest, here represented by the counting process N, is that confounding might affect the mediator and indirectly by this affects the event of interest. So this would also need to be adjusted for this type of confounding because it's an indirect way of confounding the outcome of interest. Now, if you think maybe this is breast cancer mortality, you're studying breast cancer mortality, and this is other cause mortality, you must be aware that the confounding between whatever the treatment is that you're looking at and other cause mortality, the confounding structure might be very different than all the things that you're thinking about when you are thinking of your breast cancer mortality outcome. Okay, but on the other hand, when we randomize A, this problem, or when we can randomize A, this problem goes away. For the controlled direct effect, the additional difficulty is that we want to fix by an intervention the mediator, like eliminate the competing event. And for this to be identified, we would need to adjust for any common causes, including time-varying ones, between the two types of events or the two types of processes here. So this you cannot ensure by randomization. You cannot get rid of this by randomization. So just for fun, in the colonoscopy example, we did the analysis, even though you can debate whether it's meaningful to look at the controlled direct effect of screening on CRC incidence when we eliminate death. But obviously the data, you can analyze your data, that will always give some results. So the dotted lines are the direct effects, so under the hypothetical elimination of death. The solid lines are the ones that you saw before. You can see it doesn't make a big difference, but if you eliminate death, then of course there's a bit more chance or opportunity for colorectal cancer to occur if people cannot die first. And therefore it goes up a little bit in the control group and only a tiny little bit in the treatment group. But as I say, we can't even really think about the assumptions here because there's no way how we can realistically think of a real intervention of eliminating death. Okay, does that mean we should always look at the total effect? Well, there is of course also a problem with looking at the total effect because it may going back to the dementia example, it may result in conclusions like smoking prevents dementia, because what smoking does, it most of all kills the patients first before they get old enough to develop dementia. So this is what we see in this paper. I'm exaggerating a little bit. If you look at the results here, it's really a tiny little effect, but this is just to make the point very clear that the total effect alone does not always tell the whole story. So I want to talk a bit more about mediation and how in longitudinal and survival settings, but maybe before I start with this, I wanted to give the opportunity in case there are any questions, there anything in the chat or so, Q&A so far.
Yes, there are a couple of questions, but I think one was rather early before you answer. I think you did touch upon it, but it's when you are working with screening and cancer, how do you deal with the time lead bias? But I guess that's what you did cover.
The time lead bias. So that when you ensure alignment at time zero, there is no time lead bias. So I think that's one of the main points of doing a target trial emulation. But of course, not just write a table or so. You need to ensure the alignment at time zero, and then you're ensuring that the treatment and the control group in that respect are equal, and that you don't have that type of bias then.
And then the other has to do with something that you mentioned in your paper, but also you touch upon here, and it's when you're talking about doing the confidence intervals using at person level draws. What exactly does the person level represents? And they're asking whether it's like unique IDs or rows from the pool population, or how is it done?
No, so you have to start at the very, the original population. That's where you have to do, because you want to do the bootstrap, the uncertainty over the whole procedure.
Yeah. Okay, I think we can continue.
Okay, good. So let's talk a little bit about causal mediation in longitudinal survival settings, because as you see, we've already talked about total effects and controlled direct effects, so there's something mediationally going on here. And just returning to the original little diagram where you have a treatment, and I'm being a bit vague about it, could also be time varying. It doesn't make the diagram easier to read. So let's think of it as baseline treatment, two processes, and we cover a lot of typical settings with this. So these could be two processes while people are alive, like blood pressure and kidney failure. And we've looked at this in an analysis here in this paper. but it could also be like a competing event when one is the cognitive function and the other one is the indicator for survival. Mind you, we could also be interested in something like how the relation is between cognitive function and survival, and therefore, investigate both on an equal footing. Yes, so that this is the same thing, and we've looked at some of this in some papers mentioned here. Now, I don't want to write out formally in potential outcomes and everything the definition, the usual definition, counterfactual definition of direct and indirect effects. Let me just explain a little bit with the diagrams what is going on. So the definition, according to Judah Pearl, is based on the non-parametric structural equations induced by causal diagrams. And what he then defines as the direct and indirect effects are represented by the direct path or the indirect path of the treatment onto the outcome. So this would be the direct effect, or would represent the direct effect of A on the first time survival, and this would represent on the second time survival, whereas indirect path would be anything that goes through something with the mediator first. And you can, so I'm trying to draw this here with the green one and the blue one. That's not even all of the indirect paths. So there are lots of paths that go through the mediator at some stage before they reach the survival or the Y process here. The thing is that as long as you have measured or not measured something on the pathway that is common to both, so to the direct and to the indirect setting, that is known as in the path-specific effect literature as a recounting witness, and it means that these notions of direct indirect effects are never identified, whether or not this is measured or not. And continuous time settings don't make it easier. So in a way, this is never identified, and often people just write down their assumptions with potential outcomes and don't even notice this, right? So it's often ignored in the literature. So let's look at an alternative, and not as an alternative to this problem of no identification, but also as an alternative to what is it that we actually want? We cannot eliminate death, right? So what is it that we actually want? And an estimand that is, at least in principle, compatible with a possibly very hypothetical target trial is the one of separable treatments. And this is assuming, so this is only meaningful in settings where the treatment has different components, so here the components AM and AY, that you could imagine setting separately in some trials, some hypothetical trials. And then the idea is, if you can believe in the assumption that one of these components really only goes through M and the other one goes directly into your process Y, I haven't drawn them as processes here, then this would satisfy the assumption of a separable treatment. So AM activates the mediating pathway, this component AY activates the pathway avoiding M, and hypothetical interventions setting these to different values are relevant to the research question, but observationally all of these are always identical because we only have the one value of A here. Now then the target of inference might be either I want to manipulate AM while fixing AY, that would be then a separable indirect effect, or I want to manipulate AY while fixing AM, and that would then be a separable direct effect. Okay, now you may think this is quite bonkers, this idea, but we are all very familiar with one particular example of separable treatments, and that's the placebo-controlled trials. Because what we do here is we separate two aspects of the treatment, two components, namely is it an active ingredient or not, versus does the patient know or not know that they are being treated. So these are two aspects, and we can manipulate them separately. We can give everyone the same shape of tablet, but some contain an active ingredient and some don't. So these can be set differently, and this is what is being done all the time. So it's a very familiar, actually, a very familiar setting. And other examples have been given in the literature in the meantime, for example, vaccine effects. There's a biological effect of building up the immune system, but also people change their behaviors when they know that they are or they are not vaccinated. In drug developments, we aim to develop drugs with the same active components but reduce side effects, for example, to increase adherence. So we try and separate different components that lead to the active way how the drug works, but do something else with adherence. You can also think in the colonoscopy trial of scam colonoscopies. You would do the same procedure but without removing polyps. You can also do the same procedure without telling the patient the result, so they don't know if they have cancer or not. All of this is unethical, but it's not against the laws of physics like some other S demands are. So how does this now relate to the path-specific effects of Judah Pearl? Well, it corresponds to grouping together certain types of paths. So in the separable effects, we are grouping together the blue path, so those that go into the mediating process first, versus the red path, those that go to the outcome process first. And that's what we are contrasting. So we are not looking at all direct versus all indirect paths. We're grouping them together in this way. And whether that is meaningful or not must be decided on a case-by-case basis. So identification, you can write out, I'm not being very formal here, the assumptions for identification. Essentially, you make very similar assumptions to the identifying point treatment case, but you need no confounding between the mediator and the outcome process. And then when these assumptions are satisfied, we can write out the identifying functional, which looks a bit, well, it looks exactly like the usual mediational G formula. So if you're not familiar with this, don't worry, you don't have to understand the formula now, but it's just the same formula identifying functional that you get with the different assumptions and different estimate as well. So we can estimate it in the same way as before. We've reduced it with a new story, with new assumptions to the same identifying functional. One thing to keep in mind as far as potential violations are concerned is that because we are in a longitudinal setting, we need to make sure that the frequency at which we are measuring things represent the rate at which things might change here. If we measure too not frequently enough, and this becomes an unobserved variable, a latent variable, we have the same problem as before. We have a common cause of the outcome and the mediator process, which is unobserved, and then we can't identify the effect. And as I mentioned, we have many methods already available for the estimation of the mediational G formula, and I think there's even these are not even the most recent ones, so there are new ones have been put on the market since then also. So that brings me to the last part, where I want to also show how these general thoughts about longitudinal mediation and separable effects relate back to the competing event setting. And I should say the term separable effects has been coined in this paper by Mats for competing events. I've already used it in these types of settings here, where this could be any longitudinal process, but we didn't call it like this at the time. I don't remember. So Jamie Robbins and Thomas Richardson call this the interventionist approach to mediation or something like this, because they're thinking of making really explicit how do you want to intervene to in what components here. So, but the separable effects in the literature you find mostly with competing events, but it's the same principle. So if we now look at competing events, and this is an example from the first paper that we wrote on this, where the treatment is this, I can't pronounce, DES treatment, and the event of interest was death from prostate cancer. Apparently there's a plot that isn't shown yet, and the competing event is death from other causes, which is the dotted line. So this was a randomized trial, and we are just looking at the cumulative incidences separately for the death from other causes, the dotted lines, and the death from prostate cancer. And the red lines are under the placebo. Oops. So you can see that under treatment, the prostate cancer incidence comes down from the red placebo group to the black treatment group, but the death from other causes goes up from the red placebo to the black treatment group. So is the treatment just killing people first before they can, from something else, maybe they all get a heart attack, before they can develop prostate cancer? So that would be the question here. We can consider these curves individually, the differences, for example, as total effect on death from prostate cancer, and this would be total effect on death from other causes. Okay, so this is of course a concern when it goes into the opposite directions, because you really have to wonder what is best to do for the patients. So let's assume that we have separable treatment components, that we can separate the treatment into different components, where AY activates the event of interest, avoiding the competing event, and AM activates the competing event. Now, the separable treatment effects in this competing event setting would be, for the event of interest, I want to either manipulate for the direct effect AY, so I would have two different values here, or I want to manipulate AM for an indirect effect, so I want two different values here. Okay, and again, we're looking at cumulative incidences. And this is in fact a novel S-demand. So unlike the mediational G formula that we saw for the longitudinal survival settings, which had been derived differently as well, this is for time to event with competing event settings, a new S-demand. Well, it was at the time. Now it's already been used a bit. The identification, I've already mentioned this before, especially the separability, what we need to assume is that this component AM doesn't have some other pathway to the event of interest, the process representing the event of interest, and this component AY doesn't have some other pathway to the mediating process. And otherwise, it's very similar to the controlled direct effect. In terms of the estimation, as usual, you have the two versions, and the combination of the two versions, you can either use the mediational G formula for this competing event setting, which requires modeling of all also time-varying covariates, or you use semi-parametric models using inverse probability weighting, where the weights, you can see here what is being done. You replace basically the probability where A follows the mediator by what A following the treatment, the direct effect here. Okay, let's see this in action with the example, and then I think it is also time to come to an end. With the example of this DS, which is an estrogen, you can think of this as having two different components, namely the component that suppresses testosterone and the component that is an estrogen-induced effect on the coagulation of the blood coagulation, and therefore, indeed, you can think that people maybe tend to have a heart attack or strokes more likely here. So, and there is a modified drug. Remember, I gave you an example for separable effects. It's often modified drugs that try and retain the active component in the same way as this drug, but somehow remove or cancel out the mediating component. And again, another drug that I can't pronounce, it is on the market, and the idea was to keep the testosterone suppression without this coagulation effect here. So not that we compared these drugs, it's just to say there is a story behind this, that could, for which this analysis might be relevant. So as before, I'm showing you the curves. The red curve is as before under placebo, and the black curve underneath the green curve is as before under treatment. And the green curve is now a combination where we retain the active component, but we remove the mediating component. Okay, and now the difference between the green and the black curve, that's the indirect effect, and the difference between the green and the red curve, that's the direct effect. So you can see that there is a small indirect effect via, so that the indirect effect would mean the drug kills the patient first before they can get prostate cancer, and therefore we see the difference. But there's only a small, if all the assumptions are satisfied, there's only a small indirect effect, and there's a large direct effect of the drug if we keep the coagulation okay, then the drug is doing a good job at reducing the risk of prostate cancer. Okay, so since then, so the paper came out 21, 22, and Mats, the first author on that paper, has also continued much work on this, on the theory, looking at time-varying cases, at continuous time, at the truncation by death problems, and some Stata people have also implemented the separable effects in Stata. That brings me to the end of my presentation, and I just want to make the 3 points here, 3 or 4 points here, that in time-varying settings, time-to-event settings especially, usually we have time-varying treatments, sustained treatments. We should carefully think about the causal estimands that we want. Target trials can help with the alignment at time 0, which is not obvious when you use claims data, usually not obvious, depends on the question, of course, and similar in other longitudinal and competing event settings. With competing events, I would ask everyone to really think hard about what is it that we really want, what is the estimand that we want that makes is meaningful in the subject matter context. And you may want to consider separable treatment effects as a new viewpoint. It's certainly always helpful. It prompts the elaboration of what hypothetical interventions are maybe practically relevant in the future drugs, modified drugs, etc., and what is also compatible with target trial principles, unlike other proposals like Pearl's structure equation model approach. Thank you very much, and I'm happy to take questions.